Okay, so I'm going to talk about the stereochemistry of carbon compounds in the next 20-25 minutes. Let us start. So first, let us consider a reaction where I have chosen a very simple reaction. We have an aldehyde and the cyanohydrin formation based on the attack of cyanide with aldehyde. So you can see the orbital picture of the aldehyde. So we have this is a pi star orbitals, and similarly aldehyde has two faces. So the cyanide can either attack from the front or from the back face. Based on that, we'll see that we'll get different stereoisomers. So I'll tell you what is stereoisomers. So let us consider the first case where cyanide attacks the aldehyde from the front face. Okay, so what happens there? The cyanide attacks from the front, so the nitrile group ends up pointing forward, and the hydroxyl group is ending up pointing backwards. Okay, so this is the case where cyanide attacking from the front. Now in the next case where cyanide attacks from the back. Okay, so in this case we see that cyanide, the nitrile group, is ending up in the back face, that is the face behind the paper, and the hydroxyl group is over the plane of the paper. Okay, so this is the two cases where the two faces attack take place. Now we'll see the products. So the first case where the cyanide attacks from the front face, we get a product A, and if we imagine a mirror and take a mirror image of that here, so like this one. So this is a mirror image of product A. Now we simply rotate this molecule through this yellow axis, and we get the product B. So these two, if we see product A and product B, so product B forms, as you remember from the previous slide, that it is from the attack of cyanide from the back face, and whereas the product A is from the cyanide attack from the front face. So these are non-superimposable or superposable mirror images. So these are mirror images, but they cannot be superimposed. That is, if we put one on the top of each other, they will not form the same thing. So they are different. So, and these are called the enantiomers. So enantiomer is a very important term in stereochemistry. So those are relating to the non-superposable mirror images. And the important thing is that A and B are formed in equal amounts. So two enantiomers are formed in equal amounts, and these molecules are known as the chiral molecules. So this is a slide where I introduced to you the term chiral and the term enantiomer. So these are very important in stereochemistry. So let us now go to the next one. So what are enantiomers and chirality if we define? So enantiomers are structures that are not identical, but they are mirror images of each other, and the chiral structures cannot be superimposed on their mirror image. So for real life examples, as we see a pair of hands, a pair of feet. So feet and the gloves, also the golf club. So they are one type of isomer, stereoisomer, and they cannot be superimposed on each other. So these are our chiral objects, right? Now, what happens if I have, instead of aldehyde, you take the acetone, where I have both the methyl groups, so similar groups, and then I do the same thing, that is a cyanide attack and acetone cyanohydrin formation. So here, what happens here, that if cyanide can attack from the front, we get the product C. If it attacks from the back, we get the product D. So we can see here that C and D are interconvertible by simple rotation. So that's why they are not chiral, they are achiral molecules. So this is our superposable mirror images. So these are mirror images that can be superposed on each other. So these are achiral molecules. Now there is an important relation between the chirality and the symmetry elements. So let us just name the symmetry elements first. So we have four symmetry elements, important ones. First one is the simple or proper axis of symmetry, Cn. This is a rotational symmetry element. Then we have the plane of symmetry, sigma. There is a reflective symmetry element. Then we have the center of symmetry, I. that is also a reflective kind of symmetry element. And also the fourth one is the alternating or improper axis of symmetry, SN. Okay, so let us now see what kind of operation they do. So if I consider this cyclobutane molecule, we have the G group. This is a seg-butyl group. It is a kind of a chiral group. So if I rotate this by 180 degree, and we get up the indistinguishable formation of the molecule. So they are the same if I rotate by 180. So that's why it is called the C2 axis, or simple rotational, simple or proper axis, CN. That is C2 here, because we are rotating by 180 and 360 by 180 is 2. So this is C2. Now the other one, this is the I, or inversion symmetry. So we go here and we go to the molecule and end up getting the same point, the same group in the other part. So this is the same cyclobutane which is having the center of symmetry, or I. And the third picture I have shown here is again the chiral groups are oriented like this, and we first rotate by 90 degree and then reflect a plane perpendicular to the axis. So this plane, and we get the same group. So this is called the improper axis of symmetry, or alternating axis of symmetry, and this is also a reflective kind of symmetry. So the important thing about the chirality, that it should have the rotational symmetry, but any kind of reflective symmetry present, the molecule won't be chiral. So those will be achiral. So absence of SN necessary and sufficient condition for chirality. Okay. So another reflective symmetry, reflection plane of symmetry, sigma. So we have this molecule. So you can see easily that this molecule has a plane of symmetry which passes to the central carbon atom OH and CN, and this molecule has also a plane of symmetry. If we put an orthogonal plane through the molecule, we get the reflection. So the two parts are reflection of each other. So that's why, because for having the plane of symmetry, these molecules cannot be chiral. So these are achiral molecules. None of these molecules are chiral. Okay. But if you see these molecules, which I have considered in the beginning of the lecture. So here I have two enantiomers. Those are non-superposable mirror images, and they do not contain any reflection of symmetry or plane of symmetry. So if we pass a plane like this, that one part of the molecule is not the mirror image of the other. Okay, so that's why they are non-superposable mirror images, and that's why they are chiral and they are enantiomers. Okay, so now we say the essential points about planes of symmetry and chirality. Any structure that has no plane of symmetry and they can exist as two mirror image and form enantiomers. Okay, and any structures which with a plane of symmetry is not chiral. So if it has a plane of symmetry, it cannot exist as two enantiomers, right? So those cannot be chiral. So this is a condition of not being chiral, and this is the chirality or enantiomer. So the main thing is that it should not have any plane of symmetry. Okay, so now another two important terms in configurations and conformations. So these are very important terms in stereochemistry. So what does the configurations mean? Configurations mean the way the molecules are connected, the atoms are connected with each other through bonds. Okay, so the only way we can interconvert between the configurations is to break a bond. So these are configurations because there is a different connectivity in between the atoms. So these are enantiomers. So enantiomers or stereoisomers are different configurations of molecules. They are different molecules. But the term conformations here means that the structures can, by simple rotation like this, they can change to the other structure and they represent the same molecule. So if we consider this molecule, if we rotate this, we end up getting this structure. Then again I rotate this, into this structure. So these are all same structures of the molecules, and these are different conformations of the same molecule. So these are the essential difference or main difference between the term configuration and conformations. So one should remember while reading the stereochemistry. Okay, now let us see how we can designate a chiral center, or the configurations, how can we designate as, and we have a nomenclature called R and S. So R and S is a nomenclature by, or CIP nomenclature based on the scientist name Kahn, Ingold and Prelog. These are the nomenclature of determining the configuration of the chiral center. What is the chiral center? So if we see this carbon atom, we have 4 different groups attached to this, and that's why it is chiral and is called the chiral center or stereogenic center. So we have an amino group here, we have a CO2H group here, we have a methyl group here, and we have a hydrogen group here. Okay, so now this is a natural alanine configuration, structure of natural alanine. So we see the 4 different groups and 4 different atoms. So what this rule says for determining the RNS or configuration, it says that first we have to consider the atomic number of the 4 different groups. Okay, so first we see we have hydrogen and the atomic number is 1. Then we consider methyl. This atomic number is 6 because it is connected to carbon. Carbon is atomic number 6. Then we have here CO2H. Here also the atomic number is 6. And then we have an amino group where nitrogen is there. Atomic number is 7. Okay. So according to atomic number, we can number 1, 2, and 3, 4. But there is a clash between the 2 and 3 because both are having atomic number 6. So now, how can we differentiate them? Which one is 2 and which one is 3? I have written 2, 3 here, but now I say to you what is the rule determining this, assigning the priority. Now you see here carbon is attached to the oxygen, whereas here carbon CH3 means carbon is attached to hydrogen. So now we consider oxygen having a higher atomic number than hydrogen. So this should be the higher priority 1, and so CO2H comes as second in the priority list, and then third one is a methyl, and fourth one is hydrogen. So this is the way. First we have to, while determining the structure, we have to consider the assign the chirality of the groups. Okay, so we first assign priority according to the atomic number, then we consider 1 by 1. So an amino having atomic number 7, then CO2H atomic number 6, then attached to oxygen atomic number 6. So again CH3 atomic number 6 but attached to hydrogen, so that is 1. So that's why CO2 is greater than CH3, and then we have the hydrogen as the least priority one or the lowest priority group, and this is the chiral center we talk about. Now we see how we are going to give R or S. So this one we have this structure, you see. So hydrogen is pointing up the plane of paper, the amino group is pointing downwards and behind the plane of the paper, and methyl and CO2H are on the plane of the paper. So the same rule applies here, atomic number. So we assign NH2, since its atomic number is 7, it is as 1. Then we assign CO2H as 2, and then CH3 as 3, and hydrogen as 4. The same I told you in the other slide. Now we have to rotate in a way so that the lowest priority group, that is the hydrogen, should be behind, this pointing to inside the paper. So that will be behind the plane. Okay. So if I rotate, what will happen? These 3 groups will come up. So I just rotate like this. Okay. So hydrogen is going back, right? And this is coming up. So CO2H comes up, and then Me comes up, and then again this NH2 comes up. So this 3 comes over the plane, and hydrogen goes behind the plane. Now this is the structure or the conformation we are going to use to determine R. Is it R or S? Okay. So let us see what is the rule there. Now if we see 1 is this is 2, this is 3, and now we consider mentally how the rotation occurs. So mentally we see it is rotating like this. So this is an anti-clockwise motion, right? So anti-clockwise motion that is designated as S. So this structure where we have the lowest priority group behind the plane, and 1, 2, 3. These 3 groups are oriented, moving if the rotation is anti-clockwise. that is mentioned as S. So this is a structure of S-alanine. Okay, so this is how we designate the S. It should be anti-clockwise. The 1, 2, 3 groups should be rotating anti-clockwise. Now, what about the R? It should be opposite one. Okay, so if you see this structure, what happens is that hydrogen is obviously behind the it's inside the plane of the paper, that is behind the plane of this this board. Okay, this OH is above the plane, right? CO2 is Me are on the plane of the paper, right? So we see we don't have to do anything, we don't have to rotate because it's already the lowest priority group is points into the paper. So now we again draw a mental picture how the rotation is occurring. From 1, 2, 3, we see it is rotating this way. So that is clockwise, right? So it should be designated as R. So clockwise R, and this the name of this compound is R-lactic acid. Okay. So we see that how we can designate the different cardinal centers, different configurations, and this is how we do the RS nomenclature of the molecule. So now I'm going to continue on this lecture on the next series. I'll talk about the other important things about stereochemistry. So keep on listening. Thank you. Pause.